Good morning, everyone, and welcome to our distinguished lecture. I'm very happy to have a well-known researcher as a guest, so Falko DRESSLER, who's currently with the University of Berlin, TU Berlin, is going to talk today about one of his, current research areas, I would say. So there's tons of buzzwords in the title. There's 6G, there's virtualized, there's edge computing. I mean, cars, well, this is not as new, but resilient, and edge AI. So interesting things. And well, each of those is complex. Getting them together probably is not going to be more simple. And I'm rather curious what you're going to talk about today. And without much further introduction, because if I list all your awards and whatever, then we don't have any time for your talk. I would just hand over to you. The screen is yours, the floor is yours.
Excellent. Matthias, thanks a lot for the invitation. Thanks a lot for everybody here to join for today. So my basic information I was given beforehand is this is a normal class, so we treat it as a normal class. So in a normal class, you are supposed to interrupt me any point in time when you have questions. In a normal class, I might ask questions. No kidding. Actually, I do, no? but okay, I see there is a difference between normal class and today. And so it's really a pleasure being here in Darmstadt. So I have lots of friends here in Darmstadt, which is really cool. And then joining here and making new friends, possibly, even better. So when you look at what I'm typically doing, then I'm living between different fields. So I'm living in between electrical engineering, doing lower layer wireless communications, and computer science, doing distributed systems research, and sometimes things get together. For today, I tend to shift a little bit more on this CS background rather than this wireless communications background, but nevertheless, there are interesting aspects on that too. So Matthias mentioned that this is a super complex title with a lot of buzzwords, so whenever you have research results, whenever you do a master thesis, whenever you write a paper later on, please do not add as many buzzwords in the paper title. This will be an auto-reject by many reviewers because the people don't believe that you solve all the problems in the world. If you give a talk somewhere, I personally believe it's possible. I did so today. No? So because then you open up, let's say, the floor for many question marks that you have in your mind before the talk, and some of them will be answered during the next 40, 50 minutes. Some of them will remain open and maybe provide the floor for discussions. I'd like to start. So the title was, in the middle of the title, there was edge computing. And edge computing is something that is not new at all. Edge computing is something we in research started working on 15 years ago, something like this. There was a lot of research in the field of telecommunication networks in general on edge computing. And the main motivation for edge computing is actually everything that we did before is classical cloud computing. Classical cloud computing is in the internet, since the internet as the, let's say, user-centric internet with all the World Wide Web applications, with all the video applications, with all the cloud applications started, where we just, whenever we are mobile, we want to do something, we send everything through our cellular network, we send everything via the internet to some cloud service, and you know all these cool cloud services. No? So we get everything done kind of for free. We have kind of infinite amount compute resources in the cloud, and the cloud is doing whatever we need. Some of you will have experience with that. Some of you may use pick a cloud service of your choice, do some processing in the cloud, and you essentially get it for free. Kind of infinite amount of resources that you get. The problem is that for every information that you want to be processed, you send that information through the core network of your cellular network, through the entire internet to the cloud. So where is the cloud? Physically, it's not exactly close. So typically, physically, it's typically these data centers. They are located in Alaska, Greenland, Norway. Typically in places where it's cold. So AC is not a problem, and the data centers produce a lot of heat dissipation. So it's a really problematic. But the second question you should ask yourself is, what exactly are you processing in the cloud? So some of you have experience, I'm very sure. Some of you use that without much thinking about what. No, every day you use your smartphone for tons of applications. So which of the applications are running really on your smartphone? And which of the applications are actually running somewhere in the backend cloud? And using the smartphone just as a front end for doing input and output, a little bit of processing, and doing everything else in the cloud. And of course, now all these local sensors, you get take pictures, you process pictures, you enter messages in your system, and so on and so forth. Many of these applications today, of course, they are somehow AI-driven applications. So are all these AI-driven applications running on your phone? No, this is from a security privacy perspective. Matthias, already a very nice question, but also a question of how efficient actually is this application running. If I send all my data to the backend cloud, let's assume it's processing that infinitely fast, and getting the results back is just time. So sometimes the systems feel slow, simply because the data centers are very far away. No? You know what is the most, so I switched to question mode, right? So you know what is the most important AI application that is running on all your devices? This is the time for feedback. Next word prediction. So you type something, and your device always suggests you what might be the word that you're currently typing. That is the most AI-heavy application that is running on all your devices at the moment. In not very long ago, all these applications were running in the backend cloud, sending everything you type to the backend cloud, doing some AI training and doing some AI processing, and then getting you, oh, by the way, you may want to have to type, I love you. But you don't know. Meanwhile, fortunately, many of these applications are running really on the phone. So your cell phones get AI coprocessors, and we will get to that in a second. So your end devices are getting much more, let's say, sophisticated in terms of hardware in order to run AI processes. But going back to this AI question, so sometimes you do something local, so you train a local model, but typically this is only partial training, and most of the training of these AI models, which is still compute heavy, you do somewhere in the backend cloud. Then you have to somehow merge these models, which, yeah, come on, honestly, you just have two model, let's say, versions, one smaller one trained on your device and the larger one in the backend cloud. So merging them is rather simple from an algorithmic perspective. Let's keep that in mind. But this is still rather inefficient because of the backend cloud is quite far away in terms of delay, in terms of data rates that you have. Possibly you have to pay for that, possibly not, depending on your contract types, data plan types, and so on and so forth. So this is why 15 years ago people started working on a new concept, and this new concept is called edge computing. When I say 15 years ago people started working on that, this slide says 5G edge computing. 5G edge computing is meanwhile a standard. So edge computing has been standardized some years back. We now see 5G deployments. So when you look at your smartphone now, then you may see a 5G logo in your smartphone. Part of the 5G is also mobile edge computing. So what is mobile edge computing? Mobile edge computing is the idea that you equip all your base stations, in addition to having all the communication infrastructure, you equip these base stations with compute capabilities, with storage capabilities. You install computers. And if you install these computers, the nice thing is that now you can do, if you want to process something, you don't have to go to the backend cloud, but if you're lucky, in many cases, hopefully that will be the case in some future, you just go to one of your G-Node Bs. So G-Node B is the edge, the base station in 5G terminology. So you just go to your base station, have the base station compute whatever you need, and getting you the results back. The base station is just one hop away. This is just, everything in between is a wireless channel. And 5G already now has rather fast wireless channels. So depending on where you are, we just did a nice study, so backtracking a little bit, we just did a very nice study with some colleagues in the US, all over Europe, for figuring out how fast 5G networks really are compared to LTE networks, 4G networks. So in terms of data rates, 5G typically wins. In terms of latency, interestingly, it does not win all the time. Very interesting artifact. But anyhow, so the base station is one hop away. You can connect the base station and you can do everything there. Only in very, very few cases when the base station cannot help, no resources are available whatsoever, you have to go to the backend cloud. 5G, mobile edge computing. We go back to this in a second. Let me add one slide in between. Now, if you again think of, let's say you want to, what is again the most compute-heavy application that you have is training of AI models. And if you ever worked with training, particularly training, inference is typically rather fast in machine learning. But if you do training of AI models, you need GPUs, you need a lot of power, and typically, in many cases, you don't have that necessarily available instantly on your end device. But maybe the GNOD can help here. So if this device has sufficient resources, that can help. But now the interesting thing is, AI becomes a little bit more tricky. Why that? Because now you have different instances of your models. You have an instance of your model that you have on your end device that you even possibly train and push forward on your end device. You have another version of the model that is possibly aggregated from the one that you have on your end device, aggregated with multiple users on the GNOD. And there's an even more complex, fully aggregated model version or model instance in the backend cloud. So getting everything together, unfortunately now, is a little bit more tricky. So you need to have algorithms for doing distributed AI, distributed machine learning, getting somehow these models transported from your end device to the cloud, sorry, to the edge and to the cloud, and then always doing some aggregation, for example, like in federated learning, with a lot of complications. With a lot of complications. I will talk about some of these complications at the very end of today's presentation. But let's assume we have this edge computing. Hey, come on, this is an enabler. This is an enabler for so many new applications. You have super fast processing directly at the edge, so you can immediately do tons of new applications. Now, this slide lists only very few. This is from a survey paper that I just copied on this slide. So you can do a lot of things. One of the buzzwords in my title, you remember, is cars. So maybe connected vehicles is a field where you can apply that. Let's assume we can do so. Let me show you a video. This video is very old. Basti knows this video very well. Now, what you see in this video here is cooperative driving. So you have a couple of cars in a city environment. Some of the cars driving east-west, some of the cars driving south-north. These cars are connected to a single base station. And the base station is now doing processing. So what do you need to do in order to pass through this intersection without any stopping? You need to know, well, when exactly is the other one arriving? Do I need to slightly decelerate or slightly accelerate in order to not run into an accident? So just because you see, visually see, there's no accident, no accident, no accident, no accident again, no accident again, right? In the simulation, it works super nice. So in the simulation, honestly, so getting that into real world, we need particularly one thing, and this one thing is coverage. So this is a very popular website that gives you coverage of different cellular networks in different countries and different locations. So what you see, just have a look at this violet color, that is 5G. So everything that is violet, that is covered by 5G networks. So doing this cooperative driving application in Berlin, well, it looks rather good, right? This violet. Darmstadt, somewhere here, well, not so bad. Somewhere here, maybe not. No? So that's one thing, and the other thing is we don't need only coverage in means of 5G connectivity, but we also need coverage in terms of mobile edge computing. So we need also computers there. Otherwise, without these computers, we can't do the processing. If we can't do the processing, everything falls apart. Let me add one more thing. By the way, the location of these letters is just random. This is I made it up. It's not exactly random. I put these letters at rather bigger cities in Germany. But what is very important with these letters is this 10. So let it sink. I talked to multiple operators in Germany. So I talked to Deutsche Telekom, I talked to Vodafone, I did not talk to O2. And they all mentioned, yes, we are deploying mobile edge computing now. And we are going to deploy in the order of 10 edge servers. So what I would expect is that just in the local vicinity of TU Berlin, we have 10 edge servers. Now it's 10 in Germany. So again, let it sink. Question? It's absolutely very good. It's very good question. No? The answer. So the question was for everybody who was not able to get it. Now, where is this number 10 coming from? Maybe related to something like content delivery networks, like services like Akamai and others that do services in the internet. No. Easy answer is no. The more complicated answer is nobody knows whether they will ever make money out of that. Nobody knows. And now it's investment, and this investment is, we invest into a technology that may or may not survive in the end. I'm very sure that edge computing has a huge potential. Edge computing actually, in my opinion, is a fundamental technique that we strongly need in our networks in order to kind of get to a next stage, next level, having processing distributed, not just doing communications in the network, not just using the network as a data pipe to somewhere, to a backend cloud that is located in I don't know, Iceland or in Greenland. We need local processing. We need distributed processing. Without this processing, many of our applications, and again, keep in mind, what are our compute-heavy applications? A lot of that is AI. A lot of that, actually. If you argue, I have later on another slide that I can show now. If you argue maybe in the next generation, it's maybe not AI, but we're talking about XR applications in the metaverse. But again, we are then talking about living in a virtual environment and navigating in a virtual environment, but how is this virtual environment set up? You can't transmit all this data, 3D, whatever, over the data pipes we have in super low latency. So you have to do local computing. You have to, most of that will be generated, artificially generated by, again, machine learning algorithms. There is no way around for that. Otherwise, it doesn't scale. No? So the idea is cool. The idea is very simple, actually, and the idea is wonderful. But no, we are currently seeing very limited deployment. 5G is out there. But if I say 5G is out there, please also carefully think of what that means for you. So actually, 3GPP standardizes every 2 years a new version of the cellular network standards. They are now labeled 5G. But what we as telecommunication networks researchers actually understand as 5G, that's only coming in a few years. But for commercial success, you already get this logo in your devices because it's nice. It's marketing. But besides of that, think also about maybe this mobile edge computing can also help for other things. And the other things are: do you really want all your data being delivered to some backend data center for whatever processing your application is doing? Who operates this data center? Do you trust this operator of this data center? Now, if you do that in the edge, you can of course argue, I don't trust the edge either, but you deliver only part of the data to one edge server, in the concept at least, and part of the data to another edge server, and part of the data to yet another edge server, and hopefully nobody gets the big picture. That is one thing, and there are a lot of data privacy-preserving techniques out there that can do that in an even smarter way. So maybe we need to do something else. But before we do something else, I need to add yet another buzzword from my title. So you see, there's a story around these buzzwords. And the other buzzwords in my title was resilience. And so I sidetrack for 5 minutes, a little bit arguing why we, in addition to this need for mobile edge computing, we also need to think a little, at least, about what is about the resilience of our networks in general, and particularly then translated to assuming we have edge computing deployed to our edge computing. So is it always available? I'd like to show a slide that some of you have seen already. I know that Matthias knows this slide. And many of you know at least the pictures. So this is a picture from 2006. There was a hurricane, well-known Hurricane Katrina in New Orleans, or in the area of New Orleans, and particularly hitting New Orleans, and was super critical. So many people, so literally millions of people lost their homes. People lost their lives. But not only that. Well, if you read in the news later on, first, from our perspective, all communication infrastructure was wiped out. All the energy grid was wiped out either. So there's no electricity anymore. So what can you do? And then you read tons of different articles, including articles that even satellite phones were no longer operational because to these satellites there's only very limited capacity. And if now hundreds of thousands of people switch from classical cellular to satellite, capacity is just gone. So impossible to just think of, we have satellites, it's a solution to all the problems. Unfortunately, it doesn't work. There have been some studies later on afterwards, after the fact, on this hurricane and the impact on the people there. And there was a very interesting psychological observation for what really mattered in this situation. And the observation was in the very first time, so hours after the impact, people did not care so much about getting water or getting out of this, flooded house. But in the very first moment, they wanted to tell their relatives, I'm alive. But there was no communication network. No way, no chance. Another side remark that I found wonderful actually is very shortly after this impact happened, some startup companies moved in this area and set up for the very first time the largest ever ad hoc network installation in the world in New Orleans, in the premises of New Orleans, to set up a network connectivity again. And there was a private company who sponsored a satellite uplink to connect this ad hoc network from the local New Orleans area to the internet, so that people got a little bit of communications again, but only days after the impact. So it took just time. Very interesting. So did we learn anything from this? 2006, long time ago. Very long time ago. Many of you might not even remember this time. 2021, Germany. Flooding in Ahrtal, major impacts on Western Germany. Lots of floodings. And what can we read? Sorry for that is in German only. I got this from VDI Nachrichten. Oh, what a surprise. The flooding destroyed all communication infrastructure. The flooding destroyed all energy grid infrastructure. So we were not prepared, we didn't know, we couldn't expect that. So I'm over-exaggerating on purpose a little bit, on purpose. So in the meantime, fortunately, a lot of things happened. Worldwide actually, not just here in Germany, but also, and particularly here in Germany, there were a couple of new programs research programs started focusing on resilience. There are a couple of projects running in the 6G initiative, funded by BMBF in Germany, working towards making our network infrastructure, making our energy grid infrastructure resilient to problems. One of the problem type is disaster scenario. Another problem type is security IT impacts. So that is another problem. German Research Foundation also started a program. It's called Resilient Worlds, where a couple of researchers all over Germany are teaming up together to overcome problems, to find solutions, to find new methodologies for working on that, learning from the past and trying to find a path that we can mitigate security impacts, natural disaster impacts, and even others in the future. But we are talking about fundamental research at the moment, fundamental research to early prototypes to deployment. That is a timeline, 10 years, more or less, depending on how fast some startup companies pick the early research up and try to get that into solutions. So we particularly in my group, we're working on two aspects. One aspect is you see cars again. So we're talking about mobile systems, and you will see why that is in 2 slides. We are working on the one hand side on kind of setting up, in the case infrastructure is no longer available, some kind of a backhaul network again, but the backhaul network not based on fiber optics as it is today, because this might not be available anymore, or the energy is just not available to power the converters at both sides. But instead using mobile systems. Now, and mobile systems can be really everything. Can be your cell phone, can be your laptop computer, can be the car in this picture. Just for bridging communication gaps in the network, like in a classical ad hoc network. The second thing we are working on, is the focus of today's talk, of course, doing distributed edge computing under the assumption not everything works. Under the assumption network is partially not operable anymore. Now, and when we're talking about cars, so how our cars are communicating, if you buy a modern car, so this actually communication, I mean, this is a computer on wheels. So this has compute capabilities, this has storage capabilities, it has communication capabilities. And if you buy a modern car, you at least get a 5G modem these days. It's kind of unavoidable. It's kind of hidden to you as well. So you buy something, you pay a price, and well, included is a 5G modem with some data plan that feeds you data all the time. Most of the cars have Wi-Fi these days. In Germany, DSRC is rather popular. DSRC stands for dedicated short-range communication. So it's a Wi-Fi standard, or better known as 802.11p, that was designed for car-to-car communications. But other technologies are coming. So VLC is coming, very heavily so. VLC stands for visible light communications. Wherever you use LED lights, oh, come on, so easy. You have standards already these days. You have Li-Fi, light fidelity. That is just Wi-Fi on optical links. And you can just use that out of the box by modulating digital information on top of visible light. Very efficient. You can do gigabits per second over that. You can do, of course, millimeter wave communication, so going to high frequency spectrum. Well, today we're talking about millimeter wave, so going in the spectrum between something like 20 gigahertz to 60, 80 gigahertz. People are now talking already about terahertz communications, so going below the millimeter waves. And first experiments in the field outdoors are done. So it's proven the technology works. There's tons of different problems. No? So this is research. No? So there's tons of problems we still need to solve. And I always love putting this one here. No? We have 2024 now, meaning 6 years to 2030, and I have no idea what will come up. There are so many things going on in the research groups all over the globe, and people are coming up with so cool and crazy ideas. So maybe we find something really better over the time. But let's go back to our mobile systems. Now, I have one slide showing this conceptual idea of using cars as base stations. Then I switch back to edge computing. So this is how it actually looks in Germany, at least. So this is THW. This is so National Guard of Germany. And what happens in a natural disaster is these guys are coming. They have heavy trucks being able to get into these areas safely. but first objective is, of course, to get people out who are still there, who got stuck, and later on to clean up. But they're getting there. They're getting there with these big trucks. So if these big trucks, and then there's lots of workers helping in these areas, and but infrastructure is no longer there. Why not using these big trucks for setting up some opportunistic network infrastructure among these trucks? The final one may have the satellite uplink. You have network again. How do users connect to these trucks? Super simple. You use classical techniques. You use Wi-Fi, you use LTE, you use 5G. It's so easy to have just a small cell base station on top of these trucks, and you connect to the small cell base stations. You don't even notice that base stations are no longer there because you just continue using your cell phone. But you still have a personal problem, and that is how to power your cell phone. This is not included in this story, but probably you will find solutions for that. Sometimes you find a house that still has a solar energy generator. Hopefully, at least these days, now with this lot of momentum in Germany towards photovoltaic installations. So. Edge computing on cars. Now, finally, we have the cars really in the picture. We have edge computing there. Can we do edge computing on cars? They do have compute capabilities, of course. Sounds easy. They do have communication capabilities, so to communicate with the others. Maybe so. No? There's one problem. They're moving. And you will know, so you will know whenever you talked in this class about ad hoc networking, I was told. So whenever systems are mobile, everything gets complicated. So we need to talk a little bit about this mobility and how to manage mobility and how to deal with that. Just to give you an idea, we started rather early actually working on such an idea. This is one of the early papers published in 2017 already on getting edge computing on cars. And the idea is we just follow the classical edge computing architecture that was not yet standardized 2017 for 5G, but at least lots of research was already concluded in 2017. So we knew how edge computing looks like in general, at least. And if we know how edge computing looks like in general, we have these three layers. We have the cloud, we have the edge servers, and we have the users. And usually what you do is you communicate via these dashed lines here, these red dashed lines to the edge server and eventually to the cloud, doing exactly what I mentioned before. But what about installing what we called at that time a virtual edge server? And this virtual edge server is not a physical server. It's not there, no? But it's represented by a group or a cluster of these cars. So we have a group of these cars, they team up, they force all the communication and compute capabilities they have, joining that. Well, what happens is you have a compute center, a tiny compute center, but it's a compute center. And if this compute center is made available to all the users exactly using the same API, using the same interfaces, using the same 5G technology to the end user will not even notice that it's something different. So conceptually, at least. So how do you do that? Now, again, cars are mobile. So if we, for example, team up all the cars in a certain geographical area, let's say this one, all the cars within the circle. Now, the circle is, of course, very artificial. But let's assume there is a certain area that we can define. Everybody inside this area is part of our virtual edge server. Then maybe with some luck, we have these guys here. They're standing around. They're part. They're there for kind of forever. So, there are statistics that a typical car is used for every day, 1 hour. The other 23 hours is parked, doing nothing. It's not a new observation. This is an observation that many people already did. And now we see the trend, at least in the bigger cities, that people start not owning cars anymore, but using shared car services or others. You have a question? Do you have a car? Okay. So, you have a car? I see. What is the incentive? What is the incentive spending whatever resources, no? Whatever resources, let's call it this way. Might be energy resources of your car battery, might be compute resources, communication resources. So who's willing to spend this? Good question, very good question. Yeah? I asked, do you own a car? Because my second question would have been, if you have a rather new car that has already 5G modem installed, do you know what this 5G modem is doing? You don't, no? Because it's nicely embedded inside the system and your manufacturer defines what this device is doing. You have no chance for even having a word in that. No chance to even be part of the discussion here. So that is one approach. No? So maybe the next generation of cars, let's say these shared car model, you have no say in what this shared car is doing besides when you end up being able to drive from A to B. And other objectives, of course, we did a seminar into Berlin together with some people from economics department, and we indeed also did the question, okay, what incentives we can put out, and there was very interesting. So these students then did questionnaires with people on the street. So simply asking people, under which conditions are you willing to share resources? And this was a very interesting result. So really an eye-opener for me. So some people said, okay, if I get a little bit incentive, monetary incentive, no? So then I'm willing to do everything. Some other people were saying, if I can be part of this system, if I can also use others, then of course I'm willing to contribute to the system. And some other people were simply saying, if it's good for the broader good, I'm fine. If you can use that also for, let's say, public safety systems, absolutely fine, you can use whatever you like. There was almost nobody entirely against this idea. Interesting, but of course, this is biased study. There was students from one university asking people in front of the main building of this university, so probably there's a huge bias in the population. So therefore, I don't want to generalize that, but I think the first answer was more appropriate, saying, okay, in the end, you as a user will not care, honestly, because you use that car as a tool, and this tool is working as defined, let's say. Of course, you want to make sure that it works all the time. So the car battery must not run out by supporting that. But let's go back to this moving cars. It's much from a scientific perspective, much more interesting problem. So cars are coming, cars are going. When they are coming, they are not yet part of this system. When they are going, they take everything. They let's assume they just compute an AI model, then they go away, and all the processing is nil. It's gone. It's not helpful anymore. So we need to think about this from a more general perspective, and we did a little of studies, particularly on that. Let me directly jump to a nice animation we have. So PhD student in Berlin, Panu was working on this. So he had, now let's assume we have not just one of these edge clouds, but we have many of them. Of course we have many of them, because if we want to cover everything, full 100% coverage. Let's assume the car on the left-hand side is doing some processing on this first microcloud. The other one is doing some processing for the other one. And now both move on, but of course, they can use all their communication capabilities to understand, okay, well, I'm leaving, but there's somebody else coming. Why not migrate all the tasks I have to the other guy? Now we're talking about migration of code, migration of data between these two cars. And now we can think of, is that feasible? there's a lot of work in task migration, typically done in data centers again. So migrating a job from one CPU to another CPU, from one computer to another computer. There's a lot of work in this field, and lots of this work can be reused. So you can do some pre-migration of code, so code bases is already there. You can do some pre-migration of data while it's still feasible, and in the last second you just do this last snapshotting update. So it's not so bad actually. So typically that works. And so they do their migration, and the network continues working as if nothing have happened. If there is another car coming in this direction, and if there's a car coming in the other direction. There are lots of ifs in there. So of course you will not be able to provide 100% guarantees in all these cases. Impossible. Of course, our realistic world is much more complicated. You may have structures like this, where cars are coming from different trajectories and going elsewhere. But in the end, this is a combinatorial problem, and you just need to solve this combinatorial problem, figuring out who's coming there and there and there, and which task is better migrated there or there or there. Yeah. If you're solving such a problem, you can do that brute forcing through all these possible combinations, or you again throw an AI machine learning algorithm on top of it, which by the way doesn't work that bad. So getting the same kind of a solution. So we did a little bit of this, jumping through the animations. We did a little bit of this, and then we explored success rate. So y-axis on all these graphs is success rate. So we want to get to 1. You see, 1 is nowhere there. But we wanted to get at least as close to 1 as possible. And what you need to look at is the leftmost bar compared to the next few bars. The leftmost bars is a baseline. You don't do this migration. And the other bars is if you do this migration in more or less intelligent ways. And if you don't do any migration, you are down below 20% of success rate, which is totally useless. If you do that rather intelligently, you get a speed up in the order of 300%, 400% of what you previously had. Still not reaching 1, but reaching numbers that are not so bad. 70%, here even 80, 90%, depending on how large are the data, how many cars are there, what is the interest rate of participating in the system. So it's not so bad. The only problem that we have is, now let's talk again about methodology. The only problem we have is, in order to make that this decision intelligently as possible, we need to know for how long will a car participate in our edge cloud. How long is that? So many of you have driven a car already. So when you pass an intersection and you're lucky, you get this green wave. You're in this intersection area for 10, 20 seconds. When you are not so lucky, call it this way, you're getting this red. You're standing there for 2 minutes, 3 minutes. 2 minutes, 3 minutes is kind of infinite time for computers. 10 seconds, maybe not. 10 seconds is rather short time. So we need to understand and predict how long cars spend at this intersection. This, by the way, is called the dwell time. So the time they stay in this area. So what we did is, we, as researchers, we tried to do an empirical approach to this. So we tried getting some data, just measuring that. The only place we were able to get really accurate data from is Luxembourg. So we took Luxembourg. It's the only reason why we picked Luxembourg. So there's public data available for how cars are moving. So we did some empirical studies. We did statistics on that. We figured out, okay, if we do a curve fitting for the empirical data we got, we see in Luxembourg everything is distributed according to Johnson SU. Textbook Johnson SU is skewed Gaussian distribution. Okay, so it is. We take Johnson SU, problem solved. Be very careful whenever you do statistical fitting of empirical data. Be very careful about this. So this looked like, okay, it was a peak, it must be Johnson SU. So we did the validation of this, of course, and what you see here is the validation. So we have the sample data and the actual data, and you see the shape of the curve is the same, but obviously there's a deviation still. It's not the same histogram. And that is because in Luxembourg, our Johnson SU fits perfectly in 80% of these intersections, and in 20% it's totally off. So it doesn't work. No? Doesn't work. If you take any other city, it's totally off. Do we have to do, in order to optimize our algorithm, do we have to do studies for every city and every time of the day and whatsoever again? Maybe not. No? So revisiting the problem and thinking again, what is our edge computing actually doing? Well, our edge computing is there for helping users, for solving AI problems at the edge. This is an AI problem, so we throw it to our edge computing. So a little bit of tooling first. So in order to be able to do that, we came up with some implementation of a toolkit. This toolkit combines simulation of mobility. In this case, we used well-known simulator Sumo, simulation of urban mobility, and simulation of our networking. So for an agent later on, simulation of our networking was done in a simulator called OMNet++, very similar to NS3. So some of you will have experience with that. And we combined everything under the umbrella of a very popular AI tool that is called OpenAI Gym. OpenAI Gym is a toolkit which is super easy to work with for the beginner, particularly for putting some reinforcement learning algorithms in there. So just getting as a connector, we open source the tool. It's meanwhile also used by others, and we run the same algorithm again. So what you see on this slide now is for Luxembourg and Manhattan grid as just a different street layout, as different as possible from Luxembourg. We run both our heuristic on the left-hand side, so this was this Johnson SU, versus our fully embedded AI solution. And what you see on the y-axis is just mean absolute error of the estimate. So large is very bad, small is very good, so it's just loss error. So you see, for Luxembourg, we have a loss of this value. The concrete value doesn't matter so much. And with our AI approach, we reduce this error already significantly, about 50%, to about 50% of the error, simply because we are now able to treat also these tiny intersections that were not fitting before. And in a street layout like Manhattan grid, Johnson SU didn't work at all. That's what this bar is showing, but because it's so regular, so the AI solution is perfect. You can't do much better on this side. So helps a lot. So let's take all this together and now think of generalizing. And when we generalize, we want to, of course, provide edge computing. We still want to provide edge computing, 5G edge computing. It's actually now 6G edge computing, because in 5G it will never go into the standards anymore. The next thing that will happen next year, actually, the standards for 6G are started to be written. All the preliminary research is currently being done. So it will be going into 6G, we hope. Revisiting this problem that we had before, now the only difference is that our end systems also have a lot of processing power, and the end systems have storage capabilities and communication capabilities. Why not turning the end systems into part of the edge? If you then want to do some communications, then maybe it's just instead of asking the 5G base station, which is not there, or has not edge computing deployed or whatever, we just ask another car. That works if the edge system is not there, powered off, it's hacked, it's spammed, it's jammed, or whatever, and we can still move on. So it's the idea. Well, in some cases, we may still have to go back to the edge, and we still may have to go back to the backend cloud, depending on what you do. Do you think it's feasible do we have enough compute resources available? Today it's a tough question. But already if you have a rather modern smartphone, independent of the brand, it has AI coprocessors in there. So doing very efficient actually model training for AI models. The old ones didn't have that. So if you help somebody else with training, you will barely notice it, and the other person might get a lot of benefit. The question is, what is the impact on my phone? And the phone is much more critical than on a car. Now, if my battery drains like crazy because I help all of you training your AI models, then I will be super unhappy. We have to find models for that. Very likely that will in the end really end up in payment models. If you look at cars, it's even more interesting. Let's have a look at the last animation part here. So if you think of some autonomous shuttles that are currently either experimented with, or in some cities in the world they are already driving, they have GPU capacity on these cars. It's just amazing. That's really just amazing. Also here I had a discussion with some guy from the autonomous driving department from Daimler, and they told me in their test cars, well, it's test cars, no, it's not what they really sell in the end. In their test cars, what they had as GPU capabilities, I don't have so much GPUs in my lab, in my entire lab, and I was envied just to get this car, not for driving, just putting it there stationary to use it as a compute platform for all our projects, which is just crazy. And giving you one more, which is also really cool, that is from January 2022. Now it's a little bit outdated, now already 2 years back. There was one guy who bought this Tesla, and it got in the news everywhere in the US, by the way. Got this Tesla, and he thought, I pay so much money for this car, and I'm barely using it. It's standing most of the time, it's standing around. No? So what he was doing is he hacked this Tesla so that he had access to the compute resources and started Bitcoin mining. And so he made about $800 a month for using this Tesla while it's parked for Bitcoin mining. I have no numbers how much energy this car consumed in this period, but it was very popular. No? So every newspaper in the US you opened in this time, beginning of January 2022, there was the same headline: Tesla hacked so much compute power there. And that's obviously at least now a 2 years old car. What can you do today? Think of that. Unfortunately, it's not as easy as it looks like. No? So we put all these compute resources, we have these storage resources, but how do I use it's a massively distributed system now. How do I use all these resources in a more or less acceptable way? In order to do that, we need to somehow identify which local resources are available. We need to cluster them again somehow together to one of these edge clouds, otherwise it's too complicated. That's step number one. Step number two is we need to be able to migrate microservices now from one of these CPUs to another of these CPUs. And think of when you want to do resource allocation in a classical cellular network or in the internet. What resource allocation means is typically you have a dynamic set of tasks, a dynamic set of communications that you allocate to a fixed set of resources, a fixed set of routers, a fixed set of processors. And this assignment is NP complete. So meaning there you use heuristics for doing this, for solving this problem. Now you try allocating a dynamic set of tasks to a dynamic set of resources, which is a nightmare. I'm saying that because we only have very partial solutions to this. This is a real open problem, it's a research problem. So maybe you come up with a really cool idea for solving this. I would love to discuss. So very, very interesting, lots of challenges in there. So all this resource management needs to be done by some orchestrator, but this orchestrator, what is the basis for decisions? Again, this being very, very complicated. just looking at the time, I'd like to show 2 more slides and then coming to a conclusion. So I was talking all the time about cars, and you may remember me as there was this guy talking about edge computing on cars. So what if I'm not into cars? Is that still any useful? Is that working on entirely different fields? What else is very interesting these days? Everybody talking about. No, what else is very interesting? Well, let's talk about UAVs. Everybody's talking about UAVs. Nobody's interested in cars anymore. Everybody's talking about UAVs. So in the end, it's the same problem. Very interestingly. No, so very interestingly, I have a collaboration running with a very nice guy, Kai Lee, in Portugal, and he's very much into this UAV field, and but really literally using that in the field. So he uses these UAVs for smart agriculture projects. So having many of these UAVs doing multiple jobs at the same time: sensor collection, sensor processing, sensor aggregation in this smart farming field. And what this is about in the end is edge computing. So collecting data, processing this data, and optimizing the system behavior. And optimizing the system behavior is now more than just doing something. We process something on this cars and give you the result back. No, we can even influence how these UAVs move in an optimized way, so that you reduce the flying time, you reduce the energy footprint of the entire system. So what we did, it's a super complex slide, I apologize for that. Now what we did is we used an AI approach for calculating trajectories of these UAVs, and this calculation of these AI models was done in edge computing principle, distributedly on some of the UAVs that by chance just had some resources available. So conceptually, the same thing that we did here. Let's summarize everything a little bit. And when I say summarizing everything a little bit, I mean, I hope I motivated you looking a little bit into edge computing. Edge computing is super old stuff, no? 15 years old. If you open the literature, seems like all problems are solved. But there was always an assumption, and the assumption is that you have all the resources available all the time. Maybe this assumption was not correct. And maybe if you touch this assumption, then many of the papers, many of the ideas published in these papers fall apart. So, but maybe it's time to change the assumption. So maybe it's time to think of what happens if not all the resources are available all the time. And maybe I can replicate these resources dynamically, sporadically, using whatever is just available. And the funny thing is, I started with asking what are you running in the cloud? AI models. What you're running in the edge now? It's AI models. What helps in optimizing edge computing? This is what this slide is saying. So AI for resilience, resilience for AI. You have a very nice kind of environment where you can optimize everything together. So wrapping up. I try to motivate, of course I'm here to try to motivate you for something, and I try to motivate you to think a little bit more about edge computing, but now virtualized edge computing. So this is next thing in, coming for the 6G networks. We did a lot of work in the past. There are so many other questions open. More questions open than I can even tell today. So let's team up. There's just research opportunities out there. Many of you may pick here one and there one, and contribute a little bit to our research community. Bring science forward, and that is what I would love to see from all of you at some point, at some stage, in different levels, wherever you are at the moment in your career. Hope we can discuss any further. Thank you very much for being here, for allowing me to be in here. Thanks a lot. We still have time for questions, by the way. No, don't run away. This was first.
So when comparing edge computing to, I would say, a centralized approach where I have one huge... Okay.
So when I compare edge computing to a centralized approach where I have a
huge mainframe for entire Germany. Of course, when I have applications where latency is a requirement, I could imagine that the edge cloud might be faster, but that also means that I have sufficient compute power there and not so many users using it, so that the compute part is not higher than the communication transmission part. So in terms of scalability, would it also be an maybe better approach to have a central or maybe free mainframes for entire Germany and work on really high-speed links, and the compute time is really, really slow, so you can also achieve the latencies?
Let me answer first with some words that are definitely not my words, but words that you would hear from a manager from Microsoft or Amazon, and they would say, "Of course, of course." Very simple answer. We are the ones who provide you infinite amount of resources, compute resources. We are the ones who can scale that to all demands that ever may come up. And actually, if you talk about scalability, their answer might not be wrong. Now, think of multiplexing gain they get. So you have zillions of users, and these zillions of users are coming to your compute center in not exactly at the same time, but nicely distributed over time. So you get the multiplexing gain, and the multiplexing gain is huge. The multiplexing gain is really huge. So you can design a compute center that is designed and scaled in a way according to the current needs of users. No doubt, no doubt. 2 problems left, or maybe 3. It should always be 3. So by definition, 3 problems left. One problem: do you trust your compute provider? You're giving all the data to this compute provider. I'm very sure many of you trust by definition because you're using Android phones. No, kidding, sorry. Apologies, there's no offense. So there's a lot of, people are talking about, this very interesting observation. People are talking about tiniest impact on privacy and still publish all data, but this is a fact. No? We cannot neglect that. That is one thing. The other thing is indeed latency. Latency. Where is your data center? It's not only about where your data center is geographically, but how is the connection between you and your data center? Is that connection maybe congested? If it's congested, it's problematic. Then you add latency. It's just adding latency. If the application is totally latency, that's totally latency resilient, this latency doesn't matter at all. Maybe yes, maybe still yes. But then the third question comes in, and the third question is, when you calculate, this is a very interesting question for everybody here. When you calculate the energy footprint of the centralized solution, which means you have to have all these cellular networks up and running, you have to have the core network of the internet up to a scale that you can get all the data back and forth to these data centers, and you have the data centers running. What is that energy footprint versus doing some calculation just on your phone? Just asking. No, I have no answer to this. There were a couple of very interesting studies, mainly done by an Italian group at Politecnico Milano, by Antonio Capone, and he was looking in the 4G world, how can we save or reduce the energy footprint of 4G networks by simply turning off some base stations whenever there's no demand, and increasing the coverage of other base stations. No? So, which means you get less resources, data rate go down per user, but you save a lot of energy. And then powering up these base stations only when there is more demand. It's all about energy footprint in the end. I can't give you a number because I guess this statistic does not exist even, but at least food for thought, so to say, and to consider that as a third option here too. I have seen there were some questions, so let's start. Max.
Yeah, first of all, thanks a lot for the very interesting talk and this very interesting virtual edge cloud or edge node idea. I have two questions, maybe one after the other. The first is a political question. You talked about these 10 mobile edge cloud nodes deployed in all over Deutsche Telekom, for instance. If I claim that this is a typical German innovation barrier, that like others that made us fail with very good ideas and concepts in the past, especially since even your idea, I think, will work fine if even after 10 p.m. until 6 a.m. there is at least a certain amount, of fixed infrastructure that can help a thing work. So would you agree, and do you see anything we can do about it? Maybe because it's a political issue also. Is there anything we can do on the, the regulatory or any other or plan?
I understand your question, and I'm not so sure actually. First of all, your observation is 100% correct. No? Maybe this is indeed a kind of a German thing. Let's call it this way. To be very hesitant with new technologies. If you look,
sorry, and what I mean is. Customers waiting for decent services and service providers waiting for
exactly.
Yeah.
No, so to give you another example, in the US, in some parts of the US, you already have edge computing available, but in some parts of the US, you already have 5G millimeter wave communication available, which in Germany is 0 deployment. All over Europe, by the way, is 0 deployment. But this is tiny parts in the US too. No? So they have this Northeast area and the California area, which are technology affine, and they try, where there are startup companies who try to get new ideas into the market, at least as a give it a try super early, and that works, interestingly. If you go to South Korea, this is the dream of every telecommunications person, because you have 100% 5G coverage. I don't know about mobile edge computing actually, but yes, here it is still this back and forth. I don't know. I honestly don't know. Sometimes I think we are over-regulated. So adding more regulation, now you have to put edge computers in at least cities of a population of 100,000 plus. Will not help much. Maybe making it easier for companies to play around with that. So getting a license is super complicated these days for participating in the market. So maybe reducing some of the barriers so that smaller companies can get a foot quicker into this, at least giving it a try. No, so in Berlin, we are talking since 2 years now for getting a 5G license. Campus network license, which is complicated because according to German law, the owner of the property is the one you have to talk to about these licenses. But now the university is not the owner of the land where the buildings are built on. This is the state of Berlin, and the state of Berlin thinks, yeah, maybe this university is there. Maybe somebody else may come later also and ask for something, ending up in a circle with no way out anymore. So maybe reducing some of the barriers might be a good thing, but I don't see that in Germany at the moment.
Anyway, good point. Thank you. Let me quickly add my technical question,
yes.
which is just about your opinion about something that bothers us in research. With your nice simulation of this smooth intersection, it's obvious that living in a world where you have probability-based connectivity, I wouldn't, easily want to sit in that car. So in order to be able to have a fallback of sorts, I'm not talking about algorithms, but in terms of interfaces, we have SLAs, we have QoS, we have QoE and QoI. Is that sufficient, for software developers, to talk about these things and to get a handle onto the problem of having, fallback, possibilities?
It's a wonderful.
What's your take on that?
It's a wonderful question. Now we can really talk about research again, which is much better than political questions. No? So indeed, when we're talking about CPS like cars, no? So which are super safety critical. So if there's an accident, people may get injured and even die. So of course you cannot 100% rely on one, let's say, sensor input only that is coming over an unreliable interface. And all wireless communication is by definition unreliable. So there is no, this concept of reliable wireless does not exist. So I can jam this channel, the channel can be blocked for whatever reasons, and so on and so forth. But what you can always do is you can work with a probabilistic, still working with a probabilistic information about the quality of your channel, but then get a separate input from a different source. So what all the cars are using is a local IMU that is giving you, measuring local accelerations and local feedback. What all these cars are doing at the same time is having radar sensors in all directions, at least getting a closer look about proximity of what is going on in your environment. And taking everything together, by the way, all the measurements are noisy. It's very interesting. No, all the measurements are stochastic in some way. But if you take that all together and apply that to a control system that can deal with stochastic input, then you can get a rather safe system. So we have been working together with a control theory group in Australia just on that, to get stochastic input either from the communication side and also stochastic input from a source that we haven't talked about yet, from the human input side. So maybe for whatever reason somebody feels unsafe and interfaces with the car, while this is supposed to be driven autonomously. So also you have to take somehow that into consideration. And then you have to also get a stochastic input again from a different source. And there are now, at least in the literature so far, solutions for control theory algorithms that deal with stochastic input and still give you a stable system, a guaranteed stable system. Next step, take that research, put that into prototype systems, from prototype systems later on hopefully to real systems. We are still at the beginning. But there is research in this direction, and this is very, very much progressing these days. You had another question?
Yes, I don't know if we have... So if the question is short and the answer is short, you could try.
Ask a long question, I give a short answer, I promise.
I was wondering, you talked about the cars in a mainly a city concept, so not outside of the cities, but only at urban areas. At least that was what you analyzed.
Because it's more complicated. Outside is much easier.
And my question is, if you think that the virtual edge concept would be rather more or better to realize using stationary GPUs, for example, that live at home and not in a car. So I could imagine a thing where, I don't know, one of the inhabitants of a building has their modem connected not via DSL or fiber, but via 5G. And then everyone in that building sort of communicates via Wi-Fi, you name it, and then they share their resources to form a
I promised a short answer, yes.
Okay, so is that something you're investigating, or?
We consider that too, yeah. In the end, that is privately operated edge service. And privately operated edge service, that is what the model that is currently done in the US, which works super smooth. Works super smooth under the assumption that this base station or this edge server is again always available. If it's not, for a power outage, for example, then you have to still deal with other problems. Adding everything that is infrastructure is wonderful, and improving the system quality.
Okay, thank you.
Okay, thank you very much. So at this point in time, because we will have to rely on Deutsche Bahn to bring you home safely and on time, I have to stop the Q&A. Thank you very much again, Falko, for coming to Darmstadt, for talking about interesting research challenges. And well, let's give a bit of applause to our speaker, please.
Thank you, everybody here.
Yeah. And as usual, if you're interested to do research in such an area, your master thesis whatsoever, there's a couple of doors you could knock on here in Darmstadt, because we're also working on similar topics, from control theory over edge computing, over wireless. So just, well, stay curious and knock on our doors. Thank you.